morning, everyone. So my name is Ivan Castro, and well, the title is a bit long, so I'm going to summarize with 3 key points. Sorry for that. So we are going to be talking about the multi-fidelity aerodynamics, computational aerodynamics, static and dynamic behavior, and delta kite. So I would like to start with some unsteady aerodynamic phenomena that we observe in our experimental data. So basically we have a small test bed, small scale test bed, with which we can measure the state of the kite and also the tension of the tethers, and also the aerodynamic variables, so the angle of attack, the side slip angle, and the aerodynamic velocity, thanks to a pitot tube that we bored in the kite. So we put all this into an extended Kalman filter, and then we are able to get the position of the kite. So I'm also plotting this plot the absolute velocity of the kite along the figure of 8. So you see that we do up loops. So when we are going up, the velocity is small, and when we are going down, the velocity is bigger for the straight legs of the trajectory. We can also see the kite kinematics, between the kite and the wind, and basically here we are plotting the angle of attack. And as you see, so we are plotting it for the whole figure of 8. As you see, there are like periodic changes in the angle of attack, right? And the changes are not small, because they vary between 20 and 40 degrees, which is quite a lot. And also we can get, as part of this extended Kalman filter, we can get the aerodynamic coefficient. And we are plotting here the 3 longitudinal coefficients, so the lift, the drag, and the pitch moment. And we observe that in this figure of 8, there are 2 hysteresis loops. 2 hysteresis loops, so one for every semi-figure of 8. And basically we associate this phenomenon to dynamic stroke. Recently we did a small experiment, a visualization experiment in our delta kite. So we put some tafts here, and we put a GoPro camera in the trailing edge. And this is the extrados, so the upper part of the kite. Basically, this was what we obtained. So while the kite is, so we first reached like the equilibrium point, the flow was kind of separated, because we didn't have any absolute velocity of the kite. And then we started flying figures of 8, the flow attached. And when we go up, the flow detaches, separates. And this was repeated almost very much robustly during the figures of 8, as you can see. And also we noticed at the end of this flight, we noticed that the wind conditions changed a little bit. So the wind speed, the incoming wind speed was a lot reduced. The kite was flying slower, with a much lower absolute velocity, and the flow was totally separated, as you can see, during the final part of the flight. So this is like the kind of motivation to get some simulation tools and to be able to reproduce all these phenomena. So our framework has 3 methods. So the first one, at the lowest computational cost and fidelity, is a potential flow method, and steady panel method. The second method is Reynolds-Averaged Navier-Stokes with the SU2 tool. It's open source. And the third method is a combination between both, basically. So it's a semi-empirical dynamic stroke method. It's a Leishman method. I don't know if you know it. It's normally applied to vertical axis wind turbines and also to horizontal axis wind turbines. So for the first method, I'm going to go quick. So it's basically an in-house potential flow tool. It uses the vortex lattice method approximation, and it's unsteady. So we take into consideration the unsteadiness through the Bernoulli contribution, the unsteady Bernoulli contribution in the forces, and also through a force-free wake formation, as you can see here. So this is just for comparison of the elements, 2K elements for the mesh, to compare it with the one in 4 runs. And here you have the main publications with this of this tool. So regarding runs, basically I'm not going to write any equation because they are too long, and I think you all know it. So basically I'm using the K omega SST turbulence model, the incompressible solver because the Mach numbers here are super small, a central scheme, lax predict, a convective scheme, and also for the unsteady simulations we are using a second order dual time stepping method. So we have like an outer loop for the physical time steps and then an inner loop with a pseudo iteration to converge for every physical time step. Then the mesh and boundary conditions. Basically we are imposing the no-slip boundary condition on half of the kite here, which is attached here. Then we also have the symmetric boundary condition for the symmetry plane, and then the far field boundary condition to impose the aerodynamic conditions, angle of attack and velocity. And also we are using a kinematics module developed by Fons et al. That basically prescribes the motion of the kite of some structural nodes here, and then we interpolate these positions for our fluid mesh with a built-in module of SU2. We deform the whole mesh around this position, okay, and then we solve the fluid equations, getting as an output the aerodynamic coefficient. And the third method, the semi-empirical dynamic stall one. So basically it uses PAM, okay, as a touch flow block, and then we input the kinematics. So we input the angle of attack, the change in velocity, and so on. We get from PAM the potential flow aerodynamic coefficient, and we input both the kinematics and the potential flow aerodynamic coefficient into the phenomenological dynamic stall blocks. This is nothing but a set of 3 ordinary differential equations describing the dynamic stall phenomenon, basically. And what it does is making transformations to these potential flow coefficients in order to take into account the separation and the dynamic stall phenomenon in general. And also the empirical part of this method, in this case it's going to be the CFD data, so high fidelity data. Okay, so we are feeding the semi-empirical method with this high fidelity data with a set of static and dynamic parameters. So this is what I'm saying here. This is the numerical part of the method, which is a little bit more costly, only a little bit, than UNPAM, but it uses information, high fidelity information from the CFD. Okay, so let's see some results. So regarding the static conditions, basically we set an angle of attack and then we see what happens now with the force. So here we see the CL, the CD, and the CM versus alpha for runs in solid and for potential flow in PAM in dash line. So basically we see that the zero lift angle of attack is more or less matched by both tools. This is a good indication. However, the slopes are a little bit different, and this is because in the end potential flow doesn't take into account the separation, and this kite, even at low angle of attack, has separation. You will see the detail in the next slide. The CD is underestimated by the potential flow tool because the viscous effects are not taken into account, and the pitching moment coefficient is not bad actually for a good range of angles of attack between both of them, surprisingly. So if we look at the detail and of the flow around the kite, we are plotting here the CP, the pressure coefficient distribution. So we see that this is like a joint between the two planes at different dihedral angles. And basically here we have a suction region over here, and also it triggers separation basically from here. So here normally there is a recirculation bubble that will explode at some point if we increase a lot the angle of attack, and everything else until the trailing edge will be separated. Here we are comparing the delta CP, so the difference between the intrados and the extrados for both tools, for potential flow and runs. And we see that at the leading edge, the potential flow basically overestimates a lot the suction peak here, and also in this joint region. And also for this part, for the one closer to the tips, the potential flow gives a higher delta CP. So this kind of explains more or less these 3-4 differences. Why in the previous plot the CL was much higher for UNPAM, for potential flow. And now let's go and discuss some dynamic results here. So basically we are imposing the periodic pitching in the angle of attack, change in the angle of attack. Here we have the three longitudinal coefficients. So we see that, as I told you, there is like a recirculation bubble here that at some point explodes, and then we get a hysteresis in the lift. No? We get much lower lift, lower drag, and also not a pitch down, but so the pitching moment is decreased. And here we have basically the same result, but comparing the three tools. So this is Q runs in blue, potential flow is in red, which is quite far off, and the dynamic stall tool is around the U runs actually, because it was fine-tuned with the U runs data. But the match is quite, we would say that it's quite good. Even for the pitching moment, it's qualitatively good. And also we noticed that potential flow also had some hysteresis, but the hysteresis is in the opposite direction, because the potential flow hysteresis has a different mechanism from the viscous one, basically. So here the important thing is the angular rate, and here the separation. And okay, let's draw some conclusions. So so this work is about the combining experimental simulations to understand the physics, the aerodynamics of delta kites. So we got some experimental evidence of dynamic stall at the beginning to motivate the work, and then we developed three tools. So basically potential flow overestimates the lift, underestimates the drag, but it's fast. No? If you want to couple it with a dynamic simulator, it can give you an idea of the forces. The runs is super high fidelity for steady and for unsteady computations, but it's computationally expensive. And then the dynamic stall is something in between. So actually, as we saw in the previous result, the fidelity can be considered good. Not as much as runs, but almost, and the computational cost is much lower. So I think it's a good trade-off. And that would be all. Thank you for your attention. And
thank you, Ivan. A quick question from my side. Wouldn't it be also interesting to use a lifting line method with a pre-computed polar here? Because if you run into stall, of course, the potential method will fail, will not be accurate. But
yes, for the static results, for sure.
Yeah.
For the dynamic ones, you also need to consider like dynamic phenomena of the dynamic stall.
Yeah.
For the static one.
Okay.
But actually, the difficulty here for using the 2D polars is the shape of the kite, because the kite is flat, so it's like a joint between two planes. it's very difficult to have a profile and to get this CFD data.
Makes sense. Thank you.
Thanks for the nice presentation. I have a question on the compute model. Where you take the potential flow one and then you put the dynamic stall on top. When you do that, let's say you ran it for a very high angle of attack, there's no feedback from the dynamic model that has then lower lift because it stalls. So the potential flow solution lives its own life no matter what happens in the modeling part. So the wake is not really corresponding to what the wake is.
Yes.
When will that harm the results? There's no the lack of coupling.
Yeah, if they were coupled two ways, now they are only one way. No?
Yeah.
But if they were two ways, it would be more realistic. I agree. Yeah, it's a good approximation.
Just a quick question also. What's the reason for having this shape of the kite with these?
It's the shape of the real kite.
Okay.
So it's a delta kite with a weird shape.
Okay.
They just are like that.
Okay.
I think.
Also from my side, very impressive presentation to work. I'm interested about the experiments that you carried out in the beginning, so if you could just go back to slide 3 again. No, slide 3. I was curious how you differentiated between CL and CD in low class. Because you said that you worked with a Pitot probe, right? How did you know which part of the resulting force is the lift and which part is the drag for your system? Because you didn't have force mechanism, I guess, on the.
Because we got the alpha and the beta.
How did you measure the alpha with the Pitot?
The multiple beta to this one.
Ah, okay.
Yeah.
And then you had a force meter on the field of the kite.
No, the forces were measured in the lines, so the tension, and then everything went to the extended Kalman filter, was fused, and then we got all these results.
Okay.
Yeah, but basically alpha, beta, and the aerodynamic velocity were clearly measured here.
Okay, so you just had a multi-hole Pitot probe.
Sorry?
You had a Pitot probe with many holes.
Thank you very much for a great presentation. I was wondering about the hysteresis for potential flow. You said it had a different mechanism. Could you, I don't know if you know why. Can you explain how it works?
Yes. So basically, depending on the point of rotation, so in this case it's around the center of mass, you impose an angular rate, no? And this angular rate will change you the normal wash that the kite sees. So when we are, in this case, when we are going up, the kite will see a lower angle of attack. So for a lower angle of attack, you get a lower lift. So that's why the hysteresis loop was the other way around. However, with dynamic stall, what changes everything is separation. It's not that much. I mean, the normal wash is important because it changes the effective angle of attack, but in the end, what changes the forces is the separation itself.
Thanks.
Thank you. There's no other question on Zoom, and thanks again, Ivan.